Hello and welcome to this presentation. I am Gissel Velarde and I'm very happy to be here at the NVIDIA conference presenting fraud detection systems, evaluating XGBoost for balanced and highly imbalanced data. I am working at Vodafone and we have a project which is about fraud detection. There are many types of fraud in different industries and in telecommunications as well, but the type of fraud we are dealing with is fraud that relates to any company that has to sell a product to a customer, giving a credit or a loan. So the customer will pay in small chunks, and therefore sometimes people try to use the system to get access to products and then they disappear. Sometimes there are also customers that pay for 1 month, 2 months, and they stop paying. So all these kinds of fraud scenarios are the ones that we are going to talk now. I will try to make the talk interesting for business people, executives, but I think the most important chunk of the people who is going to listen to this talk are data scientists and machine learning engineers that are the ones that are going to develop machine learning models for fraud detection. Still, some parts may be simple. I hope that you will enjoy them, and I will present some experiments as well that we did with XGBoost, because I was interested to know what happens with data imbalance. So we have different distributions from balanced to highly imbalanced, and also what happens with the amount of data, how XGBoost performs in different scenarios. Okay, before I start, I would like to introduce myself. I started my career in 2000. I studied systems engineering, then I did a master's degree in electrical engineering and project management. I worked for a while, and then I finished my PhD at Aalborg University, and this PhD was developing a machine learning based system for music analysis. Not really related to fraud, but still music has patterns, and it also has a changing environment. In that sense, I think fraud could be related to music. In 2014 and so on, we, together with my supervisor, submitted different pattern discovery algorithms which rank high at the MIREX, which is the Music Information Retrieval Evaluation Exchange. I also developed models for music segmentation, analysis, classification, and recommendation systems. In 2021, I received a teaching award for my lecture Selected Topics in Artificial Intelligence at UPB, and last year I received a Vodafone's Star Award. I work in a nice and diverse team. We have machine learning engineers, data scientists, and data engineers. Michael Beichert is our head of department. Rafael Nigot is the product owner. More specifically for the experiments I will present, Anindya, Sanjay, and Anush evaluated previous models, and Anindya, Kushbun, Joshi, Weibo help collecting the data. The other team members are relatively new, and they are working also on data pipelines. More specifically, which contents you are going to see into this talk. First of all, if you are interested in fraud detection and how it is done, or how we deal it with when we use machine learning. Besides, if you care about accelerated data science or accelerated computing, if you are into machine learning projects. As well, if you ever face the curse on imbalanced data, and we will see the experiments later on. And also if you want to know more about machine learning boosting systems performance. Different parts will be presented in different moments of the talk, and I will be guiding you through this talk. But I hope that by the end of the talk, you better understand how good can boosting systems be dependent on your data. And I will also share some useful resources for further learning. So I hope you stay until the end. If we talk about fraud, there are some estimations on how this impacts in the telecommunication sector. So the estimation is the global estimation for telecom that the revenue is $1.8 trillion US dollars, and the losses due to fraud are about a bit more than 2%. There are different types of fraud. In this case, for example, we take care of equipment theft, commissions fraud, and device reselling. So those are mostly the types of fraud we want to identify, but in any case, you could also build a machine learning model if you have the data and if you can approach the problem in such a way that you need to identify different types of behavior. Before we do a more technical overview, I would like to frame the problem of fraud detection in the following way. Look at the picture. This is a tiger. And is this a real tiger or not? How about the next picture? Is this a simulated tiger or it is a real one? And finally, look at the third picture. Is this real tiger or is it a fake one? Although we do not work with tigers, the fraud detection problem has to do with this kind of problem, trying to identify which ones are real customers and which ones are fraudsters. And fraudsters are very clever because they try to simulate real customers. They try to have the same behavior, they try to understand the system, and actually it's a very organized process in how they work. So for us, the challenge is to identify it because businesses live from good customers, of course, and if you try to stop a customer not to take your product, you are doing a very bad problem. Therefore, you want actually not to block good customers, but you also do not want that fraudsters take advantage of your products. And then, once again, why is fraud detection hard? As I said, fraudsters are continuously changing their behavior, they are inventing new patterns, they are trying different strategies. They may represent rare cases in your data, and this is a problem for machine learning because this is related to class imbalance, and algorithms will not perform at their best when they are dealing with imbalanced data. Fraud patterns may be unseen during training, and this relates to things that will come in the future, like, for example, if you do a campaign or if a new product is released on the market, or many situations that could happen in the future that never happened in the past. Another problem is it could be that you have time delay until fraud is identified. And in our case, the collection of labels could be a problem because you believe that the customer is a real customer and you can wait for 3 months, 6 months, even 9 months to be sure that someone was really doing fraud. And therefore, the collection of labels is a problem, and sometimes it depends how you collect labels because it could be based on perceptual clues, but at the end you want to base your system on something which is factual, that is really fraud. So this can take a long process. Which industries are affected by fraud? Well, telecommunications, finance, e-commerce, automotive, and I would say any company that sells products or give credits or loans to customers, and they need to know which customers are good customers and which ones are fake or fraud or an organized crime. More technically, we treat fraud detection in our case as a binary classification problem where the positive class is of extreme interest. And as I said before, the business lives from the negative cases and positive samples harm your business. Now, let's talk for some slides about evaluation in detection systems. I'm sure that many people knows about the topic, but just as a recap, because I have some examples that I would like to share with you. And now comes perhaps the most serious slide in the talk. By the way, this is a joke, but I hope it is nice for you. Just as a recap, we have a confusion matrix, and in this example, the doctor is telling the patient, you are pregnant, and this person is indeed pregnant. So this is the case of a true positive. We make mistakes when we have some tests, and in this case, this doctor did a test and did not realize that this patient is pregnant and said, you're not pregnant. So this type of mistake is called false negative because the test or the doctor was not able to identify the positive class. We can also identify correctly that the person is not pregnant, and here the doctor says you are not pregnant. And finally, we do another kind of mistake, which is the false positive one, when a doctor would say you are pregnant, but indeed this person is not pregnant. And this is the false positive mistake. As you can see in the first diagonal, we have everything correctly. The numbers will be populated when we do not do mistakes. And in the second diagonal, we have two types of mistakes, which are false positives and false negatives. Depending on the application, you may want to reduce false positives, or you would prefer to have less number of false negatives. Or maybe you want to have the same number of false positives and false negatives, as I said, depending on your application. In our case, we don't want to have a higher number of false positives, but for example, in some other applications, you would think we prefer the less number of false negatives. Just as an example, if doctors are making tests for cancer, if they do not detect that a patient has cancer, this is very costly. So maybe the doctor would prefer to send the patient for a checkup just to be sure that this person will not develop further cancer. In other cases, you would prefer to have the much number of customers possible because your business lives for the good customers, and you would prefer not to block much number of customers. And so this is just another slide on how we see the confusion matrix. The question is your data balanced? And this is very important because the class distribution really matters, and it matters a lot because the evaluation measures behave differently under balanced and imbalanced data sets. In this example, we would have the same number of positives and same number of negatives, and the system will predict some positive and some negative. So you can see that there is a fraction which it's making mistakes. In that case, we have false positives and false negatives, and in a different scenario, we would have a balanced data set, and it would behave differently when we have an unbalanced data set. So what are key performance indicators? This is a bit open question, but perhaps you would like to take a look at the confusion matrix. Indeed, in practice, if you want to automate the process, you would prefer to look at precision and recall curve instead of ROC curve, because ROC curve works good for balanced data and it's a powerful tool, but when you have unbalanced data, ROC curves are insensitive. You would also may want to look at precision at n, so just a fraction of your samples, not your whole data set. You would like to look at F-scores, F1 if you care both precision and recall, and F0.5 and F0.2 depending on your application. Another measure is the Matthew correlation coefficient. You would look at false positive rate and false negative rate as well. And maybe you would like to consider revenue and cost, and probably you would also like to consider time. Those are mainly the key indicators. For this presentation, we will only be taking a look into precision and recall, A or C, PRC curve, and also F-scores. Again, just as a recap, the baseline PRC curve can be computed as a fraction of your data, so you would have the positives, and you would have also in the denominator your positives and negatives. In precision, precision penalizes the false positives, so if false positives are 0, your precision is 1, but as false positives increase, precision will decrease. Similarly, in recall, we care about false negatives, and false negatives penalizes your recall. If you have 0 false negatives, your recall is 1, but if false negatives increase, your recall will go down. F measures is a combination of precision and recall, and as I said, depending on your application, you would take F1 if you give same weight to precision and recall, F0.5 if you prefer precision, and F2 if you prefer recall. Accuracy is not a good measure because it is deceiving, although it considers all the values in the confusion matrix, and we will see therefore some examples. Consider the first example where we have 500 negative and 500 positive, and the baseline PRC is 0.50. In this case, we will say that this classifier makes equal number of mistakes for false negatives and false positives. So if you see the gray numbers, it's the same number of false positives and false negatives. And therefore, if you compute precision, recall, and F-scores, they will be 0.5, and accuracy is 0.67. How about now we have a different configuration, and the classifier is classed in balance. So we would have 900 negatives and 100 positives, but in this case, this classifier also flags or makes 50 and 50 false negatives and false positives. Again, precision, recall, and the F-scores stay at 50%, while accuracy tells us that this classifier is really good and tells us a value of 90. Although this classifier is still making the same number of false positives and false negative mistakes. Let's take a look at example number 3. In this example, again, we have class imbalance, 900, 100, and this classifier flags everything as negative, so it does not recognize any positive samples. We cannot even compute the measure, so we can only compute recall, which is 0, but accuracy is telling us this is a good classifier, 90. Can we believe accuracy? Probably not. How about the next example, also class imbalance, and in this case the classifier flags everything as positive, so everything will be positive. This classifier is also a blind classifier. Your recall is 1, but your precision is 0.10, and the F-scores will behave as expected. So yeah, this is a more realistic way of evaluating, right? Accuracy this time is more, does a better job. But in example number 5, we have again another classifier which has high precision but low recall. And as you can see, this classifier makes 0 false positive mistakes, but is able to identify only 5 out of 100 positive samples, and therefore the precision is high, but its recall is low. Sometimes we have seen these kind of classifiers which are very precise, but they retrieve just very few true positives. So sometimes it could be good for your revenue, but you get to know just few examples. These examples just show that you have to look always at precision recall if you want to use the confusion matrix, and the combination of the F-scores is very relevant. Accuracy is very deceiving, as you have seen. Well, now let's start discussing about XGBoost and why we selected XGBoost, which stands for Extreme Gradient Boosting. Based on the literature review, you will see that XGBoost actually performs really good in comparison to other algorithms. So there is also empirical evidence by the experiments performed, and it's fast, so time is money, and we of course want to perform many experiments perhaps to be able to deliver the best results. And really, when something had good performance and is also fast, then it should be selected. So XGBoost is an ensemble of decision trees, and basically the algorithm in the first pass creates a single decision tree. So it takes the whole data it has available and creates its first decision tree. But then in a next step, it will iterate over m number of trees, and m is a number that you can define, and it builds a tree selecting samples that were misclassified by previous trees. So this is very interesting because once it has created one tree with the whole data, it will subsample and take perhaps likely those samples that were misclassified, improving that sector, then move to the next tree, improving those samples, and then moving in the next tree, and so on and so forth. At the end, what you will perhaps obtain are the boosting trees. In this example, we have two trees, and the prediction takes account of the whole trees. So it takes every tree contributes to the final prediction. So talking about related research, there is this work which evaluated the dataset called PaySim, which is a synthetic dataset that has 9 attributes and more than 6 million samples. They used a train test strategy of 75-25%, and they turned with 5-fold cross-validation. When they tested supervised algorithms, they used KNN, support vector machines, random forest, and XGBoost. And they observed that the F-score, the F1 score for XGBoost was the highest. And if you compare with the other algorithms, it is also the fastest. They also used different unsupervised learning algorithms. One algorithm that we also tested is XGBoost, and it's presented as a semi-supervised machine learning algorithm because it sometimes do not uses labels and sometimes it uses labels. But if you want to train it, you need to use labels. Although this one provides a better F1 score, it's very, very slow in comparison to XGBoost. And we took some of the algorithms listed as well, and we observed similar behavior on the data we have. Now that you said, okay, I want to use boosting trees, which boosting system can you use? Because there are different options. In the paper by the authors, they compare different boosting systems, for example, H2O, which my colleagues were using previously. And also, if you care about time, it shows that having many samples in millions, XGBoost will be the fastest. in both cases. Other features that are interesting about XGBoost is, for example, sparsity awareness, because you could have data and not all your features will have all the data. So with sparsity awareness, also the algorithms are faster to compute. You can use also parallel computing, different algorithms like exact greedy, approximate global, and approximate local. Those are algorithms that had to do with how XGBoost is selecting the data. And what else can you do to be faster? You could also use GPU computing. This is a paper from 2017 that shows that GPU computing is much faster than CPU computing. As I understand, today you could also have machines that are even faster. And in this paper, they tested with different data sets, with different sizes and number of features, and they demonstrate that at that time, GPU computing was between 3 to almost 6 times faster than CPU computing. Now let's talk about the experiments we performed. In the first experiment, the idea was to have different sizes of data, so 100,000 with a distribution of 50-50 for positive, negative, then take a smaller data set of only 10,000 and even a smaller data set of only 1,000 samples, but always having a 50-50 distribution. And then for each of those, the data sets were also distributed in these 4 categories, having 50-50, but this time reducing the percentage of positives, like 45, 25, and 5%. So from a balanced scenario to an imbalanced scenario. And the pipeline used to prepare the data was using numerical, for the numerical data, it was a scale between 0 and 1. And for the categorical data, they went over an ordinal encoder such that values unseen during training received a reserved value. When you read about boosting trees, you know that scaling should not have impact, but in the experiments we have done, scaling does have an impact and has a positive impact for a largest data set. So it would be recommended to use scaling. A little bit of code. Now I will show you, we tested 2 different XGBoost models. One called a vanilla one that you can use by importing this library from XGBoost import XGB classifier. And when you import this model, then we use the objective binary logistic. Missing one means that you assume it could be missing values in your data or non-values, and XGBoost will take care of that. We use the seed so that each time we would have the same results. For the evaluation metric, the suggested one, so the AUC-PR. And if you want to compute with GPU, you would use GPU hist. There are many numbers in this table. You can concentrate perhaps just a few numbers. So vanilla XGBoost was trained with 80%, 20% for the test set, and for the smallest data set of 1,000 samples, you can see that the positive percentage of positives, it's on the left side, so from 50, 45, 25, and 5%. In general, precision is slightly higher than recall, and the performance of XGBoost will deteriorate mostly when you have only 5% of positive samples. If you take the second largest data set, which is from 10,000, you see the same impression, that XGBoost improves a bit with more data, but you also see a drop in the 5% positives. And when you have a largest data set of 10,000 samples, again, it maintains the same picture, that it improves with the more data, but also the drop in the 5% is the largest. So for the vanilla parameters, most XGBoost default parameters were used. And for a randomized search XGBoost tuned, those are the parameters we used. So the max tree, for example, was varied from 3, 6, 12, and 20, which is the depth of your trees, the learning rate, how XGBoost will subsample data. The collapse by sample tree is how XGBoost is selecting which features will take into the training, and also the estimators, which are the number of trees you have. And just to compare which were the default parameters by the vanilla XGBoost. Why those parameters were selected for fine-tuning? Because you can tune many more parameters. I read about this publication which won a Kaggle competition, and they tune mostly those those parameters. But when we compare the RSTune XGBoost, I will show in a minute the comparison between this approach and the vanilla one. Actually, you see the same ideas, that XGBoost improves as you give more data, and also you will see the largest drop in the range of 5%. But comparing, there was not really a large improvement when using the RSTune parameters for the smallest data sets. Only for the largest data set, there is a constant improvement or a consistent improvement in the F1 score. More in a graphical way, this is what you see. So you see kind of this curve that will fall down. Interesting could be in the future to explore 25% and all this range until 5%, how it deteriorates as the data becomes more imbalanced. But the general trend is what you are seeing here. And this is only a comparison on the largest data set of 100,000 samples. Fine-tuning does improve a little bit in the F score. And actually for the 5%, that is the largest improvement in comparison to previous improvements. So is there anything we can do to improve detection accuracy for the high imbalance data set? So that was the question that we posed, and therefore there is a next experiment, which is experiment 2, and this experiment was designed to study how can we do to improve detection accuracy when your data become imbalanced. So for example, taking again a training and test set, you would train again with 50-50 and test on your data. Then we would sample the data so that if you have again 45 positives, you would train with 50-50, so training and testing equally. And we will do this also for the scenario when you have only 25% and also 5%. So trying to balance the train set. Let's see what happens, if this helps. Well, in the results, there are two observations. First, if you see the estimated F1 score, it's very different from what you obtain in test. So the F1 score, and this is the largest discrepancy is when you have a higher imbalance. So for example, 25 and 5%. So the F1 score becomes, or the estimated F1 score becomes unrealistic. And the second observation is that recall improves, but precision worsens. And in our case, we would prefer to have higher precision than recall. So in this case, sampling to train with balanced dataset did not provoke any improvements. This is another comparison, and you will see that even for the vanilla or for the tuned XGBoost, sampling was not a positive thing to test or thing to do. But we know that now that sampling does not really help. So what are the next steps? We are very interested in testing graphs because they seem promising. We have seen some previous experiments. I think graphs are challenging as well because you need to define the structure of the graphs, and depending on that, you could have good performance or bad performance. So we are still doing some tests. We want to also review different imbalanced learning methods. There are several methods, so that's one also of the goals. Perhaps checking as well if we can tune any parameters in XGBoost to help improve when you have highly imbalanced data. We are also interested in deep learning and representation learning because sometimes, as I said, the problem is with the labels, that you don't have the labels in a decent time frame. And perhaps in the future we will test also Triton and Morpheus, which may help us in the pipeline, so to help us our life easier when we are into production. And now what I promised at the beginning, here's the documentation of XGBoost. If you follow the QR code, you will find everything you need to install it and start making your tests with XGBoost. And what I think it's also important for the future is perhaps do some feature engineering. This tutorial is developed by NVIDIA and for recommender systems, but I think it's such a good tutorial that it could also help us in fraud detection. Finally, I would like to thank the NVIDIA organizers, and more specifically the reviewers, Laila Island and Christian Garbaciak, for their inputs on this presentation and their feedback. Also the organizers Bridget Johnson and Melanie Magnum. And of course, a big thanks to my team in Vodafone. This is my contact information. I will be happy to answer any questions, and also if you want to contact me, I'll be very happy to answer. Thank you.